Hi everybody, can you hear me? Yeah. So I'm Lee Humby and I run the messaging operations team as part of the Twilio Super Network, mainly working in the SMS routing and network operations space. You'll have to forgive me if I switch up routing and routing. My British accent doesn't always get that right. But I cut my teeth working for a European SMS provider where I built the routing team, monitoring systems, and completed various projects to interconnect directly with carriers all over the world. In the last 4 years at Twilio, I built out the messaging operations team, new routing products, and metrics and alerting systems to give us insight into every aspect of SMS deliverability. So today, I'm going to tell you about the systems and processes we've built to address these issues and ensure that messages that are so critical to the experience our customers have so carefully designed are delivered reliably. A lot has changed in the world of SMS. Back in the day, you needed a lot of know-how, SMPP knowledge. You had to spin up SMPP clients, binds, queuing architecture, negotiate carrier agreements, navigate complex telco regulations just to send a message. This required a lot of development and operational overhead. Now though, all you need is a credit card and a web app and you're good to go. You can start sending SMS. There's no need for hardware or domain-specific knowledge and direct carrier agreements. But in spite of it being easier than ever, messages can still fail to arrive. Despite the move to software and Twilio building software in the cloud and our customers building advanced software, we're still heavily reliant on telco infrastructure. Businesses rely on SMS more and more for daily operations, so the impact of a failed SMS can be significant. Take Airbnb as an example. They use Twilio for guest communications for SMS. If that guest cannot message the host, they can't make their booking, and this leads to poor customer experience, increased customer support costs, and customer churn. This is because messaging is hard at scale. When sending messages all over the world to hundreds of networks, all independent with different protocols, restrictions, and supported features, this becomes a real challenge. A simple REST API and fire and forget approach is no longer enough. The global SMS network can be an unforgiving place. Routes go down because of carrier outages, messages can be delayed, delivery receipts aren't reliable, content issues can arise, regulatory hurdles can cause messages to be blocked, and local rules and regulations can change at the drop of a hat. A lot can go wrong. So what do we actually mean by reliable message delivery? Well, obviously, we mean the message displaying on the handset, but also at the right time, with the correct content, and from the correct source address. And there are many factors that can prevent this from happening, and so it's important to understand a few fundamental concepts. So first of all, delivery receipts, or DLRs. What are they? These are acknowledgements passed back from the handset when a message is successfully received at the device. It's intended to confirm that the message is received on the handset, and it kind of works like this. A customer sends a message through Twilio, we pass that message to the operator then passes it onto the handset. When that message is received, the handset generates a delivery notification. This is passed back to the operator and back to Twilio so we can update the status in your console or via status callbacks. The problem is they're not always that reliable. So some operators do not support true handset acknowledgements, and instead they support network acknowledgements. This means that they generate that delivery receipt when the message hits their network infrastructure and not when it actually hits the handset. So what that means in practice is if the phone's turned off and you send a message to one of these networks, regardless of the fact that the message can't be delivered to that phone because it's turned off, you'll still see a delivered status for your message. Also, some players in the ecosystem can generate fake DLRs, and they do this knowing that customers gauge successful delivery based on the status of the message. So they actually generate one of these DLRs regardless of if they even send it on to the network or to the handset. Operators may also do this though, if they're filtering for A2P messages or spam, so that people can't game their filters. If you imagine if when they filtered a message, they give you an undelivered confirmation that it didn't get through, it would be very easy for people to kind of test with different content and different velocities and figure out ways to game those filters. So the problem is that these DLRs, there's no authentication or certification protocols for these delivery receipts, so you don't actually know when this is happening. Next up, Sender IDs. The sender ID of a message is the source address that appears on the handset when you receive that message. There are many different types of sender IDs that you might want to use depending on your use case. So there's alphanumeric sender IDs. These are normally a string of letters, but can also contain numbers. These are ideal for one-way use cases, but not for two-way because you can't reply to the message. So in the example here, we see a dentist surgery who's sending out confirmation reminders, booking reminders. They've used an alphanumeric sender ID to brand their message. Next up, we have numeric sender IDs. These are, as they sound, numbers, just like a telephone number, that you can specify as the source address, and this enables people to reply, so ideal for two-way and conversational use cases. In the example on the left there, you see the same dentist surgery is using it for users to be able to text back and confirm when they want their appointment to be, so the two-way flow works well. And the last type is pre-registered sender IDs. So this is in countries where you're actually required to pre-register a sender ID before you can send the message. So the challenge with sender IDs is not all operators support all different types. So if you're sending with a sender ID that's not supported, it may get changed to facilitate delivery, or alternatively, the message may actually fail. So if the sender ID of the message is not kept intact, at best this can be confusing for the customer, but at worst it can result in subscribers not being able to respond. In the example here, you can see that a delivery company is sending out a delivery confirmation to ask the user if they're going to be in for their delivery. Because they actually sent it with a numeric originator, but this was changed to alphanumeric, and then the user can't reply, so this breaks the use case completely. Twilio have developed Copilot to intelligently select from a pool of numbers or an alpha source address to select the best source for the country you're sending to. We also have the SMS guidelines, which detail sender ID behavior in each country. So the challenge with sender IDs is not all operators support the same features. So unless you're using the exact sender ID supported in each destination, your message is likely to fail. In the US, for example, alphanumeric sender IDs are not supported at all, whereas in France, they actually insist on using alphanumeric sender IDs or shortcodes for sending business messaging. In Indonesia, this is one of the countries where pre-registration is required. In Brazil, it tends to be shortcodes, and in the UK, it's pretty flexible. Most sender IDs go. While each country is different, you can kind of group the types of sender ID support regionally. So in Western Europe, for example, most sender IDs are supported in most countries. North America and South America, it's mainly shortcodes, while in the Middle East and Asia Pacific, you tend to have to pre-register sender IDs in a lot of countries. Another challenge we face is around concatenation. As you probably know, an SMS segment can be up to 140 bytes, which equates to 160 characters for GSM messages, or 70 characters for Unicode. Once a message exceeds this character count, it is segmented into multiple parts. Data headers are used to concatenate this message so it can be reassembled on the destination handset. It's important to get this right to ensure that your message is delivered as intended. If you don't, the message can be sent as separate segments. And when we segment a message, we're sending those to the carrier as completely separate messages. So at that point, you can't guarantee that the messages will arrive in the right order, as these could hit different parts of the network infrastructure at different times. In the example here, you can see not only was the message delivered in the wrong order, but it was also segmented midway through the URL, rendering the URL unclickable so people can't follow the link. The other thing that can happen if you don't construct the headers right and they're split over the segment of the message, it can be completely garbled. So different networks around the world have different standards, implementations, and mappings for character encoding. So for some networks, a message sent as one encoding, like GSM, may not be supported, and therefore characters are transposed to the default encoding of the destination carrier, like Latin 1. A real-world example of this that I've seen is here. So the @ symbol in GSM encoding is the same hex encoding character as the upside-down exclamation mark or inverted bang in Latin 1. So if you're sending an email address, like in this text, the @ symbol could get changed. So Twilio handled this by testing concatenation and full GSM alphabet and Unicode support when we interconnect with a carrier to as many destinations as possible. We also have dynamic encoding feature within Copilot, which dynamically adjusts encoding per carrier to ensure that messages are delivered as intended. So each country has vastly different rules and regulations and best practices for business messaging. I've already talked about how sending business messaging in France is forbidden over local long numbers and that alpha and short codes are the approved channel. But sender IDs aren't the only requirements you have to comply with. In Saudi Arabia and Indonesia, for example, each brand has to be pre-registered. This sometimes requires paperwork and always involves a lead time. There's also separate channels for OTP content, one-time passwords, and marketing content, which makes things even more complicated. In China, you actually have to register the message body template before you can start sending. So you have to give the exact content of your message, with the exception of a few variables that you can change. If you don't register this beforehand, your message can be delayed, as they can be manually screened, or fail completely. Many countries like India, Nigeria, and Kenya operate do not disturb lists, where customers can subscribe to a do not disturb register, and so whenever messages are sent, or certain types of messages are sent, these get blocked. This isn't the same as opting out, where you receive the stop response from the customer. These are centralized DND lists that are scrubbed before the message is sent. Other countries like Argentina and South Africa have times of day where you can't actually send certain types of messages. So if you're sending promotional content after 8 p.m. or before 8 a.m., this is forbidden and messages actually get queued. These rules change all the time. So in India, for example, we got very late notice that certain international brands needed to be terminated over separate international long-distance routes. This is primarily so the carriers in those countries can generate more money. The cost of those routes is a lot higher. So they insist that international brands terminating into those countries go over those routes. In China as well, for example, in October last year, due to the 19th National Congress of the Communist Party of China, the government mandated that traffic via long codes would be blocked for the entire conference. We were only given 3 days' notice. These rules and restrictions change without notice, and we can only realize when messages fail. So we've talked about some of the SMS delivery challenges. We've got delivery receipts, where you might be getting network acknowledgements or fake DLRs and not know if the message was delivered. Sender ID issues, where domestic restrictions and requirements mean you have to pre-register, and the sender ID might get changed, or the messages might fail. We've got encoding and concatenation issues, which could result in out-of-order messaging or inaccurate content display. And regulatory issues that require message body pre-registration and are constantly changing and you need to keep up with. So, how do we deal with this complexity that's inherent to the global SMS network? To do that, we built the Twilio Super Network. The Super Network is a globally distributed team, software stack, and set of processes that allow us to detect, monitor, and resolve issues in the global carrier network. The Super Network team is globally distributed, offering true 24/7 follow-the-sun coverage across the world, across all of our offices. So how do the Super Network solve these issues? Well, it starts with metrics. We developed a ton of real-time metrics, giving us insight into every possible aspect of message delivery. DLRs, while they might not be 100% reliable, still have their uses, as a lack of DLRs, delay in DLRs, or spike in negative DLRs almost certainly indicates an issue. We also have conversion rates, which I'll talk about in a minute, and we measure latency, from submit SM response latency to DLR latency, across the whole process. We track and monitor every aspect of delivery to the millisecond, from the moment when you send a message through the API, to when we do a lookup, to when we dequeue it, to when we submit it to the carrier, to when the carrier acknowledges it, to when they give us the delivery receipt, to when we give that delivery receipt back to your endpoints. This enables us to detect outages or queuing on a provider, often before they're even aware themselves. I can't tell you how much I love these metrics. Me and my team are in these dashboards every day, and it really gives us insight into exactly what's going on our network. We can drill down to the provider level, the country level, the network level, the customer level on any aspect of these metrics and see what's going on in real time. We also have the feedback API. So as I mentioned earlier, DLRs don't tell the whole story. So that's why we built the feedback API, which enables our customers to confirm to us when the messages are actually delivered. They do this when using use cases such as OTP codes, so like one-time passwords, and when the OTP code is put into their app, they actually send us confirmation that that code was entered. So then we can say with 100% certainty that that message was delivered, because the only way they could have put that code into the app was if they received the SMS. So we've got metrics into every possible aspect of message delivery, and we're monitoring these. What's next? So next we needed to set up alerting. The problem with this, though, was that the conditions were changing all the time, depending on which customers were sending traffic, their use cases, what time of day they were being sent, and we soon realized that the thresholds needed to be network specific. For example, depending on the time of day and the type of traffic being sent, there would be different baseline deliverabilities. To give you an example of this, we could take France. Outside of 8 p.m. and 8 a.m. and on Sundays and bank holidays, promotional traffic is forbidden. So for customers sending this type of traffic, after 8 a.m. every day, this traffic would be queued. This is actual normal behavior and something you need to bear in mind. Also, at night, typically the volumes are lower, and the metrics therefore become a bit more binary and noisy. So we use data science-backed regularization methods to smooth out some of the noise and cater for destinations and times of day when the volume was low. Okay, so now that our metrics and monitoring have detected an anomaly and our alerting is triggering, what happens when we detect a problem? When you're monitoring every network in the world across multiple routing products, this creates a lot of noise. At first, we were directly paging our 24/7 operations teams, and we were seeing a lot of false alerts. Not only was this a time suck for our engineers, but it also meant we couldn't be as granular or as sensitive with our monitoring, because as we got more sensitive and reduced that time to detect, it resulted in more alerts and more noise, lots of which were false, and we couldn't keep up. So to give you an example of some of these kind of false alerts, we were seeing customers sending to invalid numbers. So when they were testing their code, they were sending to dummy numbers that could never be delivered to, and this resulted in lots of failures and affected our metrics. Also, we had customers that were looping and flooding, so they had runaway code that was sending messages to the same number thousands of times in a row. And naturally, networks would start to block this as they're flooding, and this affected our delivery as well, and resulted in false alerts. Also, there were blacklists. So I mentioned some of those DNDs earlier, but also customers that have opted out. As people were sending messages to numbers that had opted out of receiving messages, the delivery rate would also go down. But we treat this as a false alert, as there wasn't a problem with the route, it was just customer behavior. So that's why we automated the initial investigation process. So rather than our alerting directly triggering pages into our routing engine and to our 24/7 operations teams, first, we sent these alerts to a testing and validation service. This service listens for alerts, and when it receives one, it triggers a real-world end-to-end test to an in-country device for the network which the alert is triggered. The system fires a test with the relevant parameters for the alert that it's triggering, simulating real-world traffic over that current routing. For example, if alphanumeric SMS was down to the Telefonica network in the UK, our system would send a message with an alphanumeric sender ID to the Telefonica network in the UK to verify whether that message was received. But we didn't just see whether it was received, we could also tell if there was any kind of delay, if the message content was changed in any way, or if the sender ID was changed as well. And the system will also automatically test over other alternative routing options to assess which failover routes would be best to mitigate for rerouting. So based on these results, we can trigger a reroute, or page an engineer, or take no action if it was a false alert. This enabled us to be far more granular with our alerting and make it far more sensitive. and it didn't result in false alerts. So now that our metrics have detected the problem, our alerting has triggered the testing system, and our verification system has fired tests to verify the alert. The system has automatically tested alternative routing options. We can take action. Usually, the most effective way to solve the issue is to make a route change and route around the problem. We can do this because we have a highly redundant network. We, of course, deploy redundant connections to all of our providers. So if one of those connections to one of their data centers or endpoints goes down, we automatically fail over to the redundant connection. But we also add route depth to all of our routing products where possible, so we're not reliant on a single provider. This means that if a provider goes hard down, or we detect latency and increased queuing to a provider, we'll automatically fail over to the next provider en route. So, we've talked about how many routing options we have, but how do we ensure we're always using the best one? Well, as well as the aforementioned metrics, validation system, and redundancy, we also have developed an intelligent routing algorithm which tests and analyzes conversion rates across all of our routing options for every network. The algorithm ingests millions of data points for the last 30 days, applying heavier weighting to the most recent data, and intelligently adjusts routing to select the best performing providers. And remember, this is using conversion rates, not DLRs, so this is actual, confirmed delivery that our customers are feeding back to us. And this algorithm is constantly testing alternative providers and brings them into route automatically if they're performing better than the current provider en route. So now that our metrics and monitoring have detected a problem, our alerts are triggering and firing off to our testing system, which is verifying there's a problem. That's making a route change or paging our 24/7 engineers. What are the results? So we measure a few metrics about all the incidents that we catch. And one of them is how many of our incidents we are detecting before our carriers are aware. And I'm proud to say that we're detecting over 95% of our major incidents before carriers have even notified us or are aware themselves. I can't tell you how many times I've got on the phone to a carrier to tell them there's a problem and they've not been aware. They just don't have this kind of, a lot of them just don't have this kind of insight into their network. So we have to show them with our metrics that they've actually got a problem. Another metric is the percentage of incidents detected before our customers. And we're currently over 97% of the incidents we detect before our customers do. And we also measure the mean time to detect, so the time from the problem starting to when our monitoring triggers, and that's currently under 10 minutes. So we're detecting more incidents, we're reducing the time to detect, and therefore also the time to resolve, and we're reducing the incidents detected by our customers. So what's next for us? Well, we're going to investigate machine learning to strengthen our algorithm. We're expanding our test coverage to include more networks. We measure this by the percentage of our traffic around the world that we have covered by test devices. We're currently at 97%, but we're hoping to get to 99.9%. We're going to look into more automation for more automated route changes, so we don't have to involve engineers as much, and also more use case testing, so we can test promotional or two-way products. Thanks for your time. That's it.